In the last few videos, we talked about a collaborative filtering algorithm. In this video, I want to say a little bit about the vectorization implementation of this algorithm and also talk a little bit about other things you can do with this algorithm. For example, one of the things you can do is, given one product, can you find other products that are related to this? So that if, for example, a user has recently been looking at one product, are there other related products that you could recommend to this user? So let's see what we can do about that. What I'd like to do is work out an alternative way of writing out the predictions of the collaborative filtering algorithm. To start, here's our data set with our 5 movies, and what I'm going to do is take all the ratings by all the users and group them into a matrix. So here we have 5 movies and 4 users, and so this matrix Y is going to be a 5 by 4 matrix. And it's just taking all the elements, all of this data, including question marks, and grouping them into this matrix. And of course, the elements of this matrix, or the ij element of this matrix, is really what we were previously writing as y superscript I comma j. It's the rating given to movie I by user j. Given this matrix Y of all the ratings that we have, there's an alternative way of writing out all the predicted ratings of the algorithm. And in particular, if you look at what a certain user predicts on a certain movie, what user J predicts on movie I is given by this formula. And so if you have a matrix of the predicted ratings, what you would have is the following matrix where the I comma j entry, so this corresponds to the rating that we predict user J will give to movie I, is exactly equal to that theta j transpose xi. And so this is a matrix where this first element, the 1 1 element, is the predicted rating of user 1 on movie 1, and this element, this is the 1 2 element, is the predicted rating of user 2 on movie 1, and so on. And this is the predicted rating of user 1 on the last movie. And if you want, this rating is what we would have predicted for this value, and this rating is what we would have predicted for that value, and so on. Now, given this matrix of predicted ratings, there is then a simpler or vectorized way of writing this out. In particular, if I define a matrix X, and this is going to be just like the matrix we had earlier for linear regression, to be sort of x1 transpose, x2 transpose, down to x of nm transpose. So I'm going to take all the features for my movies and stack them in rows. So if you think of each movie as one example and stack all of the features for the different movies in rows, and if we also define a matrix capital theta, and what I'm going to do is take each of the per user parameter vectors and stack them in rows like so. So that's theta 1, which is the parameter vector for the first user, and here's theta 2. And so I'm going to stack them in rows like this to define a matrix capital theta. And so I have n u parameter vectors all stacked in rows like this. Now, given this definition for the matrix X and this definition for the matrix theta, in order to have a vectorized way of computing the matrix of all of the predictions, you can just compute X times the matrix theta transpose, and that gives you a vectorized way of computing this matrix over here. To give the collaborative filtering algorithm that we've been using another name, the algorithm that we're using is also called low rank matrix factorization. And so if you hear people talk about low rank matrix factorization, that's essentially exactly the algorithm that we've been talking about. And this term comes from the property that this matrix X times theta transpose has a mathematical property in linear algebra called that this is a low rank matrix. And so that's what gives rise to this name, low rank matrix factorization, for this algorithm. It's because of this low rank property of this matrix X theta transpose. In case you don't know what low rank means, or in case you don't know what a low rank matrix is, don't worry about it. You really don't need to know that in order to use this algorithm. But if you're an expert in linear algebra, that's what gives this algorithm this other name of low rank matrix factorization. Finally, having run the collaborative filtering algorithm, here's something else that you can do, which is use the learned features in order to find related movies. Specifically, for each product I, really for each movie I, we've learned a feature vector xi. So, when you learn a set of features, you don't really know in advance what the different features are going to be. But if you run the algorithm, empirically, the features will tend to capture what are the important aspects of these different movies or different products or what have you. What are the important aspects that cause some users to like certain movies and cause some users to like different sets of movies. And so maybe you end up learning a feature, where x1 equals romance, x2 equals action, similar to an earlier video, and maybe you learn a different feature, x3, which is the degree to which this is a comedy, learn some feature x4, which is, some other thing. And you have n features altogether, and after you've learned features, it's actually often pretty difficult to go into the learned features and come up with a human understandable interpretation of what these features really are. But in practice, the features, even though these features can be hard to visualize, can be hard to figure out just what these features are, usually it will learn features that are very meaningful for capturing whatever are the most important or the most salient properties of a movie that causes users to like or dislike it. And so now, let's say we want to add just the following problem. Say you have some specific movie I, and you want to find other movies J that are related to that movie. And so, well, why would you want to do this, right? Maybe you have a user that's browsing movies and they're currently watching movie J. Then what's a reasonable movie to recommend to them to watch after they're done with movie J? Or if someone's recently purchased movie J, well, what's a different movie that would be reasonable to recommend to them for them to consider purchasing? So now that we've learned these feature vectors, this gives us a very convenient way to measure how similar two movies are. In particular, movie I has a feature vector xi, and so if you can find a different movie j so that the distance between xi and xj is small, then this is a pretty strong indication that movies j and I are somehow similar, at least in the sense that someone that likes movie I may be more likely to like movie J as well. So just to recap, if your user is looking at some movie I, and if you want to find the 5 most similar movies to that movie in order to recommend 5 new movies to them, what you do is find the 5 movies J with the smallest distance between the features between these different movies. And this could give you a few different movies to recommend to your user. So with that, hopefully you now know how to use a vectorized implementation to compute all the predicted ratings of all the users on all the movies, and also how to do things like use learned features to find what might be movies or what might be products that are related to each other.